Okay, we're going to take a closer look at the pressure dependence of the Gibbs free energy. And so through one of the thermodynamic potential relations, we've got dg dp at constant t is equal to the volume. And so if I want to then know, by the way, I should emphasize y'all should know the difference of when you need to take a derivative and when you need to take an integral. So you can get to this you can make this step if you make the assumption, trip over the plant. If you make the assumption that your process is going to be under constant temperature conditions, you can go from the partial derivative of g with respect to p to the integral, which is really undoing. It's called the antiderivative. dg is equal to vdp. So if I want to know how does my process change when I change the pressure, I can say, all right, well, dg is equal to integral VDP. Now there's going to be two different scenarios. You can either say, well, V is independent of pressure, or V is a function of pressure. So you have two options. Now think about when you'd have one system versus another. In this case, when is the volume independent of pressure? When is it not? So let's assume it's independent of pressure. This becomes V times delta P. And if it is dependent on pressure, well, now we need to know, well, what is V as a function of P? That should be a V. So we'll need to know what that equation of state is. So this top one, I should say this is going to be for liquids and solids. Most of the time, you could have a solid or you could have a liquid that does have some Gibbs changes with pressure, but for the most part, you can say that this is essentially equal to VDP. I'm going to put an approximate there too. So you can approximate that the volume is independent of pressure. But in this case, for gases, let's make life happy. Let's assume that it's an ideal one. So this means that delta G is going to equal integral of nRT over P dP. This should look familiar, just slightly different arrangement. So delta G is equal to nRT log PF over PI. Go team. This is when we are thankful that the system is an ideal gas. So one of the things that you'll see that Atkins does is he breaks this up into delta G is equal to G of pressure 2 minus G of pressure 1, such that if you want to then say log P, I'm going to use the same notation, pressure 2 over pressure 1, this can then become G of pressure 2 is equal to G of pressure 1 plus nRT log P2 over P1. And so if you know you start at, say, some sort of standard condition, say 1 atmosphere, and you want to know how much does the Gibbs energy change as you shift to a new pressure, this is going to be the relationship originating from your delta G that you got back from partial derivative. Okay, so now I want to relate Gibbs and temperature. And I want to know if I have Gibbs as a function of temperature, what would the plot look like? And would it be the same for solid, liquid, or gas? So one of the things I want to start with is partial G, partial T at constant pressure. This tells me this is what my how my Gibbs energy changes as I change temperature at constant pressure. That is equal to negative entropy for any substance. That's pretty cool. So we can relate this directly to entropy. And I'm going to take a step here, and I'm going to skip the derivation of how this works. But I do encourage you to look in Atkins. So you can also say that the change in the Gibbs energy, partial T at constant P, is equal to minus delta S. Notice what I've done here. And I'm going to emphasize this is a non-trivial addition. It's not just that I decided, oh, I'm just going to make this delta G. That's cool. No, it's a page of notes to get there. But you're looking at how this changes from going, so delta G of the products, G of the products minus G of the reactants gives us our delta G. Okay, the same way that you would have Hess's law for enthalpy, you can use the same thing for your Gibbs energy of a reaction. So if you have a delta G of reaction going from reactants to products, now you have not the system progressing or changing as you just change temperature or pressure. You've got two different systems that are linked through the chemical reaction. Okay, and so this is, again, non-trivial, but we're going to go ahead and use this and be happy. Okay, so if I then say that delta G is equal to delta H minus T delta S, I would hope then that if I were to take, and then from here I can solve, so minus delta S is equal to delta G over T minus delta H over T. Okay, so I've just solved for this delta S. Everyone follow me? All right, so this tells me then that partial delta G partial T at constant P is equal to delta G over T minus delta H over T. And I think I'm off by negative. Nope, I'm good. Go team. Okay, so now I'm going to explore the partial G partial T from this relation that we just derived, and I'm going to relocate minus delta G over T is equal to minus delta H over T. Okay, so the goal is I'm going to explore this a little bit, and then you'll see where I'm going, hopefully, when we get there. But the goal is to look at how does delta G change with temperature. Okay, so I'll say delta G and temperature. So I want to know how much does the temperature affect delta G with respect to T at constant pressure. Okay, so this is an aside. There is no way you would have known how to do this, or you'll know how to do it, but there's no way that you would have known to do it. I'm showing it to you as a way to demonstrate some of the benefits of looking at these problems from multiple angles. Okay, so I want to know, well, let's explore this delta G over T for a second and how it relates, how it changes as a function of temperature. Okay, so product rule, I've got 1 over T partial delta G over T, partial T at constant P plus, let me make sure, yeah, so delta G partial T of 1 over T at constant P. Okay, so this equals, I'm just going to rewrite this part, 1 over T partial delta G partial T at constant P minus delta G over T squared, because if I were to take the derivative, the partial derivative of 1 over temperature, that gives me a negative 1 over T squared. So that's where I get this value here. Okay, so now I'm going to simplify this a little bit. So this equals partial T delta G over T at constant P. I'm going to multiply both sides by temperature, and I'm left with T partial T delta G over T constant P is equal to partial delta G partial T at constant P minus delta G over T, because I've multiplied the whole thing by T. These T's cancel. This becomes 1 over T. Cool. Does this look familiar at all? Go team. So now I've got this relationship is just minus delta H over T. So I can then say I've got T dt of delta G over T is equal to minus delta H over T. Cool? Then I can move my T back over, and I have how delta G per temperature changes is equal to minus delta H over T squared. This is known as the Gibbs-Helmholtz equation. And it's an incredibly important equation because this is relating, you really could think of it as a normalized change in Gibbs per temperature, delta G per temperature, how this quantity changes as a function of temperature. So I could say this is delta G over T as a function of T And then I want to look at how does delta A, or when I plot this, then I can get the delta H from part of the plot itself. Okay, so this is a very important relationship. Go team, and you will play with this in your homework, but this is the Gibbs-Helmholtz equation. And I believe that does it for Focus 3. Yay! So hopefully this has been helpful in seeing the different ways you can approach some of these thermodynamic potentials, and we will talk in class extensively about how to relate them all. Go team.